Good? Okay, alright, it's good to hear. Alright, so today we're going to cover Chapter 6, and then on Wednesday we'll cover Chapter 7. On Friday we have an exam that will cover 1 through 6, okay? You'll have homework today that will be due on Wednesday, and then the Chapter 7 stuff that I cover on Wednesday will be due the Monday after the exam, okay? We got you'll have a lab today, and I hope I fixed the code so it will work this time. If our markdown still does not work, I will just give up, and you can I'll just give you regular old R labs to copy and paste into a Word doc or something like that. But I'm hoping the R markdown stuff will work this time. Okay, any questions and stuff before we move on? Good? Okay. Feeling good on all the stuff we've covered so far, chapters 1 through 5? Okay, so today in chapter 6, we will be covering the normal model. So the normal model is a theoretic distribution, but the shape of the normal model often is useful for describing lots of data sets that we see in real life. Okay, so the normal model, I guess it would be comparable to saying there's a theoretic probability that a coin will land heads 50% of the time. And it's useful for helping us understand the probabilities of a coin flip. Okay? And so, of course, if you flip any coin a finite number of times, it will not necessarily land heads 50% of the time. But still, that understanding of the theoretic side is useful for understanding a coin flip. In the same way, the normal model tells us how common certain values should be, or how common or uncommon certain values should be, and it's useful for helping us understand real-life data that fits the normal model. Okay. The key thing about the normal model is that everything is based on z-scores. Okay, so with the normal model, so I guess I'll write some stuff. Okay, so the normal model is
That might take a while to...
everything in the normal model depends on what we call a z-score. The z-score, and this is a definition you should learn, is the number of standard deviations a point is from the mean. So just let's start off real simple. If I say human height, or let's say for US males, the mean height is 5'10". It's closer to 5'9.5", but just for simplicity, we'll say 5'10" or 70 inches. If I say the standard deviation of height, or not if, but I'll just say the standard deviation for height is 3 inches. Okay, so the z-score is the number of standard deviations a point is from the mean. So let's say I say someone is 73 inches tall, so 6'1". What is this person's z-score? Positive 1, okay? And if someone is 5'7", 67 inches, that person's z-score is negative 1, okay? So I guess a z-score is signed in that if it's above the mean, it will be positive. If it's below the mean, it will be negative. So a man who is 67 inches has z-score negative 1. Fair enough? Okay, and everything in between. So if I say someone is 65.5 inches, what's the z-score?
Negative 1.5.
Yeah, this would give me a z-score of negative 1.5. Is that okay for us to see? All right, and so what you guys have been doing, but I'll put in formula form, is that z is equal to whatever your point is minus the mean and divided by the standard deviation. Okay, so where mu is the mean and sigma is the standard deviation. Whenever you talk about a theoretic model, you use the Greek letters mu and sigma for the mean and standard deviation. When you talk about samples of data, you would use y bar and s for the mean and standard deviation. Okay, so I will say for theoretic models, use this, and for actual data, I guess we could say z is equal to y minus y bar over s. These are equal or equivalent, and it doesn't really matter. I'm not very nitpicky about this. But as you read your text or do problems or look at things, I don't want anybody to be confused about this. Okay, and if I say someone has a z-score of positive 2, a man has a z-score of positive 2, how tall is this person? What's that? 76 inches. Okay, so z is equal, if z is equal to positive 2, then the height is 70 plus 2 times the standard deviation, so 76 inches. 6'4". We feeling good? Okay, great. So with this, once we turn things into z-scores, we can use that understanding to, I guess, to make statements. Okay, so the normal model looks like this, okay? And I'm going to start off with what we call the standard normal model. So a standard normal model has mean 0 and standard deviation equal to 1. So if a point has a value of 2 in the standard normal model, what is its z-score? 2, okay? So on the standard normal model, whatever the value it is, that is the z-score, okay? So if the value is 0.765, the z-score is 0.765. So 0 goes in the center, because it's the mean, and somewhere around here, this is 1, and equally distant in the negative direction is negative 1. Okay, so that would be z-scores of 1 or 1 on the standard normal. And if this is that, then this would be 2, and this would be 3. And going in the opposite direction, we have negative 2. And my picture is not perfect, but something like so. Should go straight down. So if I were to shade everything under the curve, and I were to say that is equal to 100%, or the total area under the curve is equal to 1. All right. Total area under the curve equals 1. So if I shade everything to the left of 0, how much would I have shaded? 50%, okay, 0.5. So if I shade everything to the left of 0, I would get 0.5, and things of that nature. All right, so this is what we call the empirical rule. And it's kind of a rule of thumb for any data that is unimodal and symmetric. Okay. And it's all based off of the normal model. We say if a data set is unimodal and symmetric, then about 68% of the data, so a little bit more than 2/3, but I guess for all intents and purposes 2/3 is fine. About 68% of the data is within 1 standard deviation of the mean, or has z-scores between -1 and 1. That's what it means to be within 1 standard deviation of the mean. It means your z-score is between -1 and 1. Okay, and so if I were to shade everything in between 1 and -1 here, that would represent about 2/3, 68% of the total possible area under the curve. Next rule is about 95% is between -2 and 2. And almost 100%, okay, about 99.7, so almost 100% is between -3 and 3. So this gives us an idea of what is considered a large z-score versus a small z-score, or typical z-score, I should say. So if things are, in general, our rule of thumb is that if things have z-scores greater than 2 or more negative than -2, we might consider that point to be unusual. Because 95% of data has z-scores between 2 and -2, so anything beyond that would be considered part of the either, I guess only about 1 in 20 points would have z-scores beyond 2 and -2. That might be kind of our rule of thumb for what we would consider unusual. And if anything has a z-score greater than 3 or more negative than -3, we would consider that highly unusual, as for most unimodal and symmetric data sets, nearly everything has z-scores between 3 and -3. Okay. And so applying that to our understanding of male heights in the United States, okay, so we said the mean is equal to 70 inches, or 5'10", and the standard deviation is equal to 3, all right? So if I say 68% of US males have heights between what? Blank and blank. What would you say? 67, so 5'7", and 73, so 6'1". 95% of US males have heights between what and what? 64, so 5'4", and 77, so 6'4".
76.
I'm sorry, 76. 76. Doing my math wrong. Okay? And does that kind of match our intuitive sense of heights in the United States? Would you say about 95% of adult males that you meet today are between the heights of 5'4" and 6'4"? Something around that? It seems like most of the people you know, most of the men, you know, probably between those heights. And then 99.7, so the vast majority would be between 61 or 5'1" and 79, so 6'7". Okay, and sure, are there men who are outside that range? Yes, but are they common? Not really. Okay. All right, let's just check your understanding. What if I ask the question about what percentage of men are shorter than 5'7" or 67 inches? I think I heard somebody whisper it to him or herself. What would we say?
16.
About 16%. Now, how am I getting that? Okay. Well, we said 68% is between 1 and -1, which leaves how much outside of 1 and -1? 32%. But that 32% is split between the stuff that's lower and the stuff that's higher. And because it's symmetric, we would have half of that, so about 16% down here, and about 16% up there. Can we see that? We're good? Okay. This is why I love UCLA, because in my other class, it's like I have to spend the whole period just getting students there. But here we go. All right, so this is great. Okay, but what if we have things in between? So what if I say, what percentage of males, of US males, are shorter than 66 inches? This question becomes not so easy to answer, okay? All we know is that that number should be less than 16%, okay? Well, this is where our handy-dandy z-table comes in. All right, so if you have your textbook, then flip to the back pages in the appendix to page, I want to say, you know what, I have the instructor edition, so my pages are probably different. But in my book, it's table A10, appendix D, table Z. It's page A110 for me. It's probably not that for you. You have it open to that page. What is that page in your textbook right there?
A64.
Okay, so if you have your textbook, it's page A64, and you see this crazy table with numbers, like a lot of them. And it's not a complete listing, but it's a pretty thorough listing of z-score probabilities. Okay, so there's two pages to the table. There's a negative table and a positive table. Okay, and so let me just copy kind of what part of this table looks like. And it starts off at negative 3.9, and it goes 0.00, 0.01, 0.02, 0.03, 0.04, so on and so forth in that direction. And this goes negative 3.9, 3.8, all the way down to 0.0. So if you have your textbook, this is useful. I guess I should have made photocopies, but I didn't. I apologize. You'll figure this out. You guys are smart. You guys you'll get this. Okay. So anyway, what we do here is we take this height, 66 inches, and we turn it into a z-score. So what would the z-score of a man who is 66 inches be if the mean is 70 and the standard deviation is 3? Okay, so the z-score would be how many standard deviations we are from the mean. So I would take the height, 66, subtract off the mean of 70, and divide that by 3, and I would get negative 1.33333. Dot, 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 dot. Is that good with everyone? Okay. And so we would look up this z-score in our z-table. Okay. Now the z-table only goes out to 2 decimals of precision, so I would have to round this to 2 decimals. And I would say z is equal to negative 1.33. And to look that up, I would go to the row that's labeled negative 1.3 and to the column that says 0.03, because if I combine those two numbers, I would get negative 1.33. And so when I look up negative 1.33, the number in the table is 0.0918. Okay. So those of you who have your book, is this matching what you are looking? Yeah. Okay, good. Good. And we understand how this works then. So what this table gives you, the table always gives you the area to the left of a cutoff line at this point, okay? So the table always gives you the area to the left. To the left of the cutoff line. Well, at least our table does. You might take another statistics course. This is probably the most standard or usual way of using a table, or writing a table, but some textbooks make their tables differently. Okay. So anyway, the table always gives you the area to the left of the cutoff line, and so what we are essentially saying is that I have a normal model, and we're graphing z-scores. So it says if I make a z-score at negative, or cutoff line at z equal to negative 1.33, and I shade everything to the left of that, the amount that I have shaded is 0.0918. And that would be the answer to my question right here. What percentage of US males are shorter than 66 inches? The answer there would be 9.18%. Based on our z-score and table. Yes.
Will we have this table for the test?
Yes, I will provide you with the z table. You do not have to memorize or construct or copy this into your note sheet or something like that. Yes.
What is the top axis again?
The top of this, so basically, it's the entire table is a listing of all the numbers from negative 0.0 to negative 0.01, negative 0.02, negative 0.03, so on and so forth. But instead of just having one giant list, they've made a grid of the listings. And so basically you are combining this number with this number to create a 2 decimal number. Okay? So if I wanted to look up negative 2.04, I would go to the row negative 2.0 and the column 0.04, and that would be the number that corresponds to the area to the left of negative 2.04. Okay? What about the positive?
Would those be on a different table?
Yeah, there's 2 pages to the table, and the positive side does exactly the same thing, okay? And you just have positive numbers. Yes?
This only works for symmetric data?
This only works for normal model data, okay? So this z table applies only to the normal model. So somewhere on there it has to say it follows a normal model. Yes?
If you're using the positive table, will it give you the area to the right of the
It always gives you the area to the left, okay? So all the numbers in the negative table should be less than what number? Should be less than 0.5, okay? And all the numbers in the positive table will be greater than 0.5, okay? And so the most extreme value is negative 3.990, and it says 0.0000. It's technically not 0, it's just rounded to 4 decimal places, it's 0, okay? And so if I were to look up what percentage of males are shorter than 67 inches, if I wanted to get a more precise number, what z-score would I look up?
-1.
I would look up z is equal to negative 1.00. And anybody who has his or her table can tell me what that is?
0.1587.
0.1587, okay? And so when we use the table, we see it's not exactly 16%, it's 15.9%, 15.87%. That's close enough for us to say 16%. Okay, so let's You guys don't have a table, so not all of you have a table, so I guess if I were to give you some exercises right now, we'd all get stuck. Okay, well, I guess I'll just do a few more demonstrations of this, okay? And I'll try this out. Okay. That's good. Do you guys remember how to construct a box plot? And where do we draw our cutoff lines that separate usual from unusual, or usual from the outliers?
1.5, like that's 1.5.
Okay, so when making a box plot, the fences go or appear are at it's Q3 plus 1.5 times the IQR and Q1 minus 1.5 times the IQR. So let me ask, what percentage of data in a normal model are beyond the fences? So here's a normal model. We're going to go with the standard normal model. And what we want to do is we want to figure out where do the fences go on the normal model. Okay. So, well, first off, where does Q3 and Q1 exist? Q1 is equal to what? The 25th percentile. So if I draw a line at Q1, how much is shaded to the left of Q1?
25%.
25%. Okay, so if I draw a line at Q1, how much is shaded to the left? This would be 25%, 0.25. So in this case, I want to find out the z-score that corresponds to Q1. So what is the z-score that corresponds to Q1? Okay, so to look this up, what z goes with Q1? Okay, so to do this, I'm going to go to the z table, but do I look up 0.25? No, I look up 0.25 in here. I'm looking for a number as close to 0.25 as I can, and I'm going to find the z-score that gives me 25% to the left. Does that make sense? Okay, this is what we call the reverse reading of the normal table. So sometimes you are given a measurement which you turn into a z-score and you look up the area. Other times you're given an area or a percentile and you look that in the table to get the z-score, and if necessary, you turn that back into a measurement. Okay, so if you have your z-tables, tell me, what is the z-score that gives me a number as close to 25% as possible?
Negative 1.96.
I think you are looking up 2.5%.
Oh.
Okay, so you would end up at the row negative 0.6 and the column 0.07. Okay, and if you look up negative 0.6 and the column 0.07, the number that you end up with is 25.14%. Okay, you won't actually find 25% exactly. You'll find 0.2514, and you also find 0.2483, okay? These are going to be the two numbers that are closest to 25%. So the true value is going to be between 0.67 and this one corresponds to 0.08. So something in between there, we're just going to go with the one that's closest, and that will be z is equal to negative 0.67. Okay, so what z goes with Q1? That is z equal to negative 0.67. Does that feel okay? Okay, so that's just saying if I draw a cutoff line at z equals negative 0.67, the area that I have to the left of that is 25%. What about Q3? What would I have to look up to get Q3?
0.75.
The 75th percentile. Okay, so I want to find in the table on the positive side the area, the z-score that's going to give me 0.7500. Okay, and what is the z? What is that z-score going to be? Positive 0.67. Okay, and that's because the table is symmetric. Okay, so if I have 25% over here, then I can get 25% over to the right, which I don't actually look up in the table. I look up 75% to the left, and that would be z is equal to positive 0.67. Is what I have done okay so far? Okay. So what is the IQR for a standard normal distribution? So what we found is that Q1 is equal to z equal to negative 0.67, and Q3 is z equals positive 0.67. So that tells me that the IQR is 1.34. And so using this, I can find the z-scores that correspond to my upper and lower fences. So my upper fence has z-score equal to positive 0.67 plus 1.5 times the IQR of 1.34. The lower fence has a z-score equal to negative 0.67 minus 1.5 times the IQR of 1.34. So in other words, it's just a negative version. Let me grab my calculator. Okay, so this gives me a z-score of 2.68 and negative 2.68. Are we still okay? And so now, to answer this question, what percentage of data in a normal model are beyond the fences or would be flagged as outliers? Should we make a box plot? I want to find what is the area to the left of 2.68 and negative 2.68. So how much is shaded over here and how much is shaded over here? Okay. So if I go to the table, the area shaded beyond negative 2.68 is equal to 0.0037. And over here I would also have the same, 0.0037. So if I add those two together, I have the total area. Total area beyond 2.68 and minus 2.68 is equal to 0.0074. So what percentage of data in a normal model are beyond the fences? 0.74% or 0.0074 as a proportion. I'll let this sink in, or if you have any questions. Yes.
If the area under the curve wasn't 1, how would we find the percent?
Okay, the area under the curve will always be 1.
Because it only works with the normal model.
Yeah, the all probability distributions require that the area under the curve be 1. Okay, because the curve represents, I guess, the probability that certain values would appear. Okay, and so probability can never be greater than 1. So the total area under a probability distribution will always be 1. Okay. If we were to make a box plot, for a US male height, where would the upper and lower fences be? Again, the mean height is 70 inches and standard deviation equal to 3 inches. So what we found in the previous problem, so from the previous problem, we see that the upper fence was located at 2.68 and the lower fence is at negative 2.68, the z-scores. And this would apply to any normal model, okay? Because any normal model essentially fits the standard normal model, just if we turned everything into z-scores, right? So the normal model says the z-scores for the upper fence and lower fence are at these locations. And so the question now is, what is the height that corresponds to these two z-scores? So the upper fence, so if I say z is equal to y minus mu over sigma, okay, what I have here is I have the location of z, which is 2.68. I don't know the height that I'm actually looking for, but I do know that the mean is 70 and that the standard deviation is 3. So if I multiply this through, I get 8.04 is equal to y minus 70. So I get y is equal to 78.04. So this would be approximately 6 foot 6 inches. And on the other hand, over here, I get y is equal to 61.96. So about 62 inches, 5 foot 2. So according to our normal model, US males who are taller than 6'6" or shorter than 5'2" might be considered outliers. if we were to make a box plot and use the rules for upper and lower fences. Is that okay? All right. So you have some exercises in your homework that ask you to find measurements and things based on the normal model using z-scores and things of that nature. Again, the normal model is useful for understanding data. So if we have an idea that something might follow the normal model, so if we say something is unimodal and symmetric, the normal model often serves as a good approximation for those data sets. Okay? And based on that,